Data structure using C++, Module 5, Session 7. So today's session, we will talk about how to insert an element onto the binary search tree. In the previous session, we already figured out the method to search an element present in a binary search tree. So here, the same concept could be used here for inserting an element. So we need to search whether the element, the key element over here, does it exist in the binary search tree? If it's available, then at that position addressed by the key element, the meaning or the pair value, the value associated with the key has to be inserted. So that's the first thing. I repeat, the first step is to search whether the key which you are having along with, does it exist in the binary search tree. If it's available, then the position shown by the key, at that position its value should be added. Value would be available at the second component of the structure field would give you the value associated. The first component would give you always the key associated with it. There is one more situation when you're trying to insert an element. The element may not exist in the binary search tree. In this case, you may have to create an extra node. You may have to create an extra node, and the whole structure, that is the meaning as well as the word, or in this case the key as well as its value, should be inserted onto that node. And we need to figure out which is the best possible position in the binary search tree where this node should be connected to, or where it has to be connected. That we need to figure out. The location for providing the connection has to be figured out, and for that we will be making use of a pointer. So the program which we talk about in a while is pretty much similar to the method search which we have already seen, that was to find whether the key does it exist in the binary search tree. Fine. Now let's discuss the program with both example considered. The first example which we will consider is the scenario. This is the first condition wherein the key element is 20 and the value associated with it is W10, and the same structure was given to you, and the same structure we had used for searching for a pair existing in the binary search tree. Now this 20, when you look at this binary search tree, 20 is available, which means the key is available in this binary search tree. In that case, the associated value for this key, the new value to be inserted, has to be at this node, because 20 is already there. So this W8 has to be replaced, and it W10 should go and get placed over here. That's what we are doing here in insertion. One more method. Let's assume that what if the value is 30. So the value 30 for the key doesn't exist in this binary search tree. So in that case, what we need to do is we need to search whether it exists. So when you use the method search, then it says that the search would be unsuccessful because the key is not available. Okay, 30 you don't have it anywhere. So you need to find which is actually the best position where you fit 30, or how do you create a node and how do you create a link to that node with some other nodes. So here when you observe this tree, so we can come to a conclusion. This is actually the right position where you can create a node and establish a link between the 30 and its parent would have 25, because we expect 20, 25 and 30 implies it's a binary search tree. Other elements are possibly correct, but the inserted element has to be inserted in such a way that the rule for binary search tree doesn't get violated. Fine. So that's the second stuff. That's what you have. If the search is successful, we must replace the old value will be the value associated with the pair, or the first value. That's a word is having a meaning. Word implies, for a dictionary, word and a meaning. Understand, word is key and meaning is its value. So replace the old value with the new value. Okay, and if it's unsuccessful, then we need to create a node, and in that node the key value as well as its value both should be fitted in the node, and we need to understand where exactly it should get linked. Okay, now let's try to discuss the program. So here, this is your main program, binary search tree insert. So this program insert method takes the pair. So the pair is having component, two component. Okay, the pair dot first and the pair dot second. Fine. Now the situation right now is the pair dot first, the key element, the pair dot first is 20. Okay, let me replace, I'll not confuse you. This is the pair first dot first. uh, Fine, this is the pair dot first value 20, and it's the pair dot second value is w10. Okay, let's not look at this now right now. So I'll just say that this is the value, and this first the pair dot first is actually the key value which you are searching for. Okay, and this is having two information. This is the value and this is the word. Okay, word and meaning. So the pair is having 20 as well as w10. The pair dot first is just 20. Okay, let's understand in that way. Okay, now first what we have to do, compare. So what basically the value is 20. 20 is there, so what you have to do, search method says that compare 20 with the root which is 50. Then we observe that the element which you're figuring out or finding out is lesser, so you have to go to this region. This is your region of interest. Then again you compare 40 with 20, because the root element for this left subtree is 40, and 40 is also greater 20. So again you move over here. 25 is compared with 20, then finally 20 and 20 are compared. Then you say that this is actually the node which you're looking for, and there w10 has to be replaced. So this program is pretty similar to your search method. Now let's discuss this program here using this. So first what we do is we create two pointers, p and pp. Now I'll just tell you, suppose if you think that the element, if it exists, if the element exists in the binary search tree, then this piece of code is fair enough. This piece of code is fair enough to run the program, and this occurs only if the element is not existing. If the search is unsuccessful, then you have to undergo this process. If not, this process is fair enough to insert a element. Okay, now first what we do is we create two pointers, p and pp. So p will be pointing to the root of this binary tree node, and this binary tree node is of this form. Okay, so this is your first situation. So p is pointing to the root is this main node, and p is also pointing to the same place. Then we check we check whether p not equal to null. Now the p value is not null, so p is having an information, it is not null. So what we have to do, we compare the element value. So how do you compare the element value? So p of element we have to examine. So first pp is made p, so where p points, make p also point to the same point. So that is done in the next iteration that is shown. Okay, now p was pointing here, so pp will also point here. Okay, now we will check whether the pair dot first is less than p element dot first. So what is there in the pair dot first? The pair dot first you have 30, and 30 is less than p element dot first. Why? P element dot first is having a value 50. So your search is this region, right? So what we do, this is true, so we do p should be made as p left child, so make it point to the left child of p. The left child of p is, if this is where the p points, the left child of p would be here. So this is the left child, so here p should point. So this would be the this would be the structure after iteration, after second iteration. Okay, after second iteration. So actually that is not shown. Let's explain it with respect to only one element. So here p points, and pp is pointing here. Okay, next what happens, again we check, we go back, p is not equal to null because p will be pointing here. So if p is not pointing there, then pp will also point here. Okay, assume pp and p both are pointing to this node. Now again, the condition is the pair dot first is less than p element dot first. So this is true again, because now the pair dot first is 20 itself, but right now element p of element is 40. So again you have to go to p of left side. So p will be pointing here. So again, over here when you come back, p is not equal to null, which means pp will also point to the same point. So p as well as pp both points here. Now the element over here is 20, and that would be compared with 20. So 25 is greater. So again, this is actually the, you have to again traverse. So p would go here, pp was here. Again you go back and you check p is not equal to null condition it is. So in this case, you check the condition is the pair dot first, is it less than the p element dot first. Now the situation, this is false because it is equal to condition. Then we compare, is the pair dot first, which is 20, is it greater than p element dot first. Both are equal, so again this is false, which means this is actually the search is successful. Okay, so you have to replace the old value by the new value. So what, how the replacement takes place? So p element dot second, p element dot second happens to be this field. Okay, this is the field p element dot second. So there the pair dot second, which is this w10, should be replaced with. So you have that command written here, p element dot second is equal to the pair dot second return. So it returns completely, this will be returned back, which means the insertion has happened. So that's the case number one, wherein we assume that the 20 exists in this binary search tree. Now let's look at the situation wherein the key dot first value, or the pair dot first value, or it is a key value 30, and this is not there in your binary search tree. So how this program would give you which is the best node where the 30 should be fitted in. Okay, now let's understand step by step. This is important. Now when you look at this binary search tree diagram, so you can come to a conclusion, this is actually the best position where 30 has to be located. So let's see how you get it. Okay, now you will make use of the pointer pp. So first case is similar, 30 you have. So 30 would be compared with the root value. So root, make p point where the root is. That's correct. Okay, so p is not null, first case. That's correct. pp is made p. Okay, pp is also pointing where p is. Right now p is pointing to the root, and pp will also point here itself. Okay, and we check the pair dot first, is it less than p element dot first. So that's true, so you need to go, p will be uh, p of left side. So now when you look at this structure, this is where the p is, this is where the p is, and this is your pp is. Okay, so right now p is pointing, pp is pointing here, it is trailing by p by 1 unit, and pp is pointing here. Okay, next what we have to do now, the pointer is shuffled, it's pointing here, key element is 20. So again compare the pair dot first, which is 30, with the p element dot first. Okay, so you have this condition here, if the pair dot first, so which is 30, is it less than p element dot first. So p element dot first value is 40, the condition is true, it is true, so you have to shift, which means uh, now right now this is the current position, pp goes here, pp goes here, pp earlier it was pointing, pp p was pointing here and pp was pointing here, and now the situation is this value is greater than 30. So this is your range of search for 30. So again p should point here, and that is done using this structure, and now pp is trailing again one unit by p. Okay, so now this is actually the value. Now what happens here, 25 you have and 30. So when you look at this scenario, this value 25 is lower than 30, so it's not something you go to the left side, instead you have to visit the right side of p, right? So in that case, let's see how this functions now. Now the pair dot first, which is 30, and you have p element dot first, which is equal to 25. So this condition 30 is not less than 25, instead it is greater than, which means the pair dot first 30 is greater than 25. So this condition is correct. So p will become p of right child. Visit the right child of the p. Now p was pointing here and its right child is null. This is not having any right children, right? So it is null. So p is null, and pp is also pointing to this position now. Okay, now the situation is this: p points here and pp would point here. Both will be pointing to the same node earlier. Now after the condition is met, when the condition is true, p is pointing here and it is null now, right? So in that case, what happens is p is null now. So when you try to return back while p not equal to null, since it is null, you come back, break this while loop, come back here. Now you can get a conclusion, or I'd say something like you get the correct information where exactly the node has to be placed. So that information you'll be getting now. So that is given with the help of pp. So just understand, pp gives you that position where exactly you need to fit the node. Next step is to create a binary tree node. Now this one statement is going to create a node of this form. Okay, so it is going to create a node with values 30 and w9, and this is not linked, and we give it a name as new node. Okay, the name of the node is new node, so it is created using this form. So we write binary tree node, new node is the name and it is a pointer to a node, and here we use new command and we use binary tree node pair, node pair with the pair dot first and the pair dot second. Everything you insert onto this node, binary tree node pointer. It's not a single value. The node elements are not single. They have two elements, the pair and the pair dot first and the pair dot second. So this instruction, one instruction is gonna give you this structure, but link is not yet established, and right now this is the scenario. pp is pointing here and p is null, it's not pointing to any of the node. Okay, now what we have to do is, since pp of right child, if I use pp of right child, if I use, that's actually the exact position, or that's where the connection should be established. If you want to connect this new node, then pp of right child is actually that command which you need to write in the program to create the connection between these two nodes. Now let's see how the connection is established. Now new node is created. Okay, then we go back here. After that, when we check if root not equal to null, now root is not equal to null, this condition is executed. Suppose initially if there is no element, because binary search tree definition also says that the elements can be empty, so tree can be empty. Suppose if it's empty, then you will have to create a node, and you have to, that new node should be inserted at the root position itself. If not, it should be placed where pp is pointing. Okay, so this condition is not valid now because tree is not empty. So if the pair dot first, is it less than pp element dot first, we check. So right now the pair dot first is 30 and pp element dot first, what is pp element dot first? Pp element dot first, that is 25. So 30 is not less than 25, right? It is greater, which means it's right subtree where you need to go, it's not left child tree, which means this condition is false. Then else command will be executed, which means pp of right child is actually the position where the new node should be connected to. So that's what makes this connection. Now pp of right child is this pointer and it is connected to the new node. So that is done with the help of the command pp right child is equal to new node. So now the binary search tree insertion is complete. That's all happens, and finally you have an instruction here, that is the last instruction else. This condition is not correct now, because if root not null, this is done, so pp, so root is equal to new node. So this is for insertion into the key. So here not null condition is executed, so this else condition will not be executed. So because tree is not empty, so this instructions will be running, and finally else this goes tree size becomes tree size plus plus, because the elements in the tree will be one more now, hence the tree size should also grow. That's the program for insert.